Hello, guys. Welcome back to Bare Metal Life. Today, let's dive into one of the most important topics in embedded systems memory and microcontrollers. But before we get into any theory, let's start with some code. That is void add void. Inside a bracket, integer a, b, c. Let's give values to a is equals to 10, b is equals to 5, and c is equals to a plus b. Close the bracket there. Now, look at this simple function here. We declare three variables, that is a, b, and c. We assign values to a and b, and then store their sum in c. Nothing much fancy though, but here's the question. When we declare these variables, where exactly do they live? Are they stored in flash or they stored in RAM? If you have ever asked yourself that question and weren't 100% sure of the answer, this video is the one for you. By the end of it, you will have a rock solid understanding of how memory actually works inside a microcontroller. Now, let's get into it. Now, as our reference microcontroller for this video, we'll be using STM32F103C8T6. It's based on the ARM Cortex M3 architecture that comes with 64 KB of flash memory and 20 KB of RAM. And inside the Cortex M3 core, it has 16 registers, each 32 bits wide. Each of these memories has a specific job. Each one stores a different kind of information at runtime. And by the end of this video, you will know exactly what goes where and why. Now, let's begin with the flash memory. Flash is non-volatile, meaning when you power off or reset the MCU, the data survives. Nothing gets erased. Now, Flash has an interesting characteristic here. It is fast to read but slow to write. The MCU can read from Flash very quickly, and it can even execute code directly from Flash. This is called XIP, execute in place. No need to copy code anywhere else before running it. But writing? That's a whole different story here. To write even a single byte to Flash, you first have to erase an entire 1 KB page, and only then you can write. Well, you cannot just go in and change one byte. Erase the whole page first, then write. That's why Flash writing is so slow. And there's one more important limitation for Flash has limited life. You can typically only write to it around 10,000 times. Some higher quality Flash can go up to 100,000 write cycles. After that, that too even wears out. So now the question is, what actually gets stored inside Flash? Firstly, that is .text. This is your code. All your functions, your program logic, whatever you write in C after compilation lives there. The second one is .ro data, that is read-only data. This includes your constant variables, string literals, and the interrupt vector table. Third one there is .data. This holds global and static variables that have an initial value. Their initial values are stored here in Flash at startup, and we will talk more about what happens to them at runtime in just a moment there. Look at this line. That is integer x is equals to 5. This is a global variable with an initial value. Well, here's something most beginners don't know. The value 5 is actually stored in Flash. But when the MCU boots up, the startup code copies it over the SRAM so your program can read and modify it at runtime. Okay, so now X lives in two places. Its initial value sits in flash and its runtime copy runs in SRAM. This is a critical thing to understand there. Now, let's talk about flash memory in STM32F103C8T6. The flash memory on this chip starts at address 0x08000000 and ends at 0x0800FFFF. That gives us 64 KB total, which splits into 64 pages of 1 KB each. Well, remember this. When you want to erase, you erase one full page. That's 1 KB minimum. You cannot go smaller than that. Also, different MCU might have different flash starting addresses. Now, the next one here is SRAM. Let's talk about it. SRAM is a volatile memory, meaning when you power off or reset the MCU, everything stored in it is gone. But what it lacks is persistence. Though it makes up in speed, SRAM is fast for both reads and writes, much faster than Flash. And unlike Flash, there is no write limit. You can read and write to SRAM as many times as you want. The only catch here is it's small. On our STM32F103C8T6, we only have 20 KB of SRAM. And that's actually true for almost every MCU out there. You will always have less SRAM than flash. Note that always. One more important thing for SRAM is DMA accessibility. The DMA controller can transfer data directly to and from SRAM without involving the CPU at all. That's a big deal for performance. Now, here's where it gets really interesting. And this is one of the core concepts you need to understand. Do you remember integer x5 from earlier? That global variable with an initial value? At boot, the startup code copies that value from flash into SRAM. From that point on, your program reads and modifies X inside SRAM. The copy in flash never changes. It's just the source of truth at startup. This section in SRAM is called .data. But what about variables with no initial value? Something like integer counter? In this case, MCU is smart about it. It doesn't waste flash space storing a zero. Instead, these variables go into a section called .bss in SRAM. At startup, the MCU simply initializes the entire .bss section to 0 automatically. Your variable gets a fixed location in SRAM, which starts at 0 and is ready to use. On the STM32F103C8T6, SRAM starts at address 0x20000000. That's where your .data and .bss section both live at runtime. Well, now you might be wondering, how does the MCU actually know where .bss is and how to zero it out? This happens through something called the startup code, also known as the reset handler. Well, here's the sequence. The moment you power on or reset the MCU, it does not jump straight to main brackets. Before that, it runs a small piece of assembly code called the reset handler. Inside that reset handler, three things happen in order. First thing, copies the .data section from flash into SRAM. Those initial values we talked about, integer x is equals to 5. This is the moment they get transferred. The second one is it loops through the entire .bss section in SRAM and fills it with zeros. Every uninitialized variable gets zeroed out right here before your code even starts. The third one there is only after both of these are done. It finally calls main brackets. So by the time your first line of code inside main brackets executes, dot data is loaded, dot BSS is zeroed, and everything is exactly where it needs to be. The MCU is fully ready. Why this matters for embedded developers? Well, to understand this, you must know if you ever write a bootloader or port to a brand new MCU, you are responsible for the startup code yourself. If .bss is never zeroed, your uninitialized variable won't start at zero. They will have whatever garbage was sitting in SRAM. That's a very real and painful bug. Now, let's dive a little deeper into this. I'm going to declare a few variables, and as we go, I will show you exactly where each one gets stored in memory. First, let's write integer I. Do you notice here that it appears inside the .bss section? That's because this variable is declared but not initialized. It has no value assigned to it yet. Next, let's write character A is equals to 10. You see, this one shows up in the .data section which exists in both Flash and SRAM. That's because it's a global variable that has been initialized with a value. Now, let's add constant character B is equals to 1. As you see here, this lands in the .ro data section of Flash. The reason? It's a constant. Its value can never be changed. Since it's read-only, it simply stays in Flash and doesn't need to be copied to SRAM. Now, let's write a function void add void open bracket integer a is equals to 5 integer b close the brackets there. Anything declared inside a function is called a local variable. Local variables only exist within the function they belong to. They are created when the function is called and destroyed as soon as the function returns. All of these local variables are stored in the stack area of SRAM. We will explore the stack in much more detail later. However, if you declare a variable outside of any function, making it a global variable, the rules change. If it carries an initial value, it gets stored in flash memory, and the best part is any function in your program can access that. Alright, now let's talk about one of the most important concepts in embedded systems, the memory map. A memory map is basically a blueprint that tells us what lives where inside our microcontroller. Every region of memory has a fixed address range, and the CPU uses this address to access everything from your program code to variables to hardware peripherals. Let's go through each region one by one, starting from the bottom. The first one, flash memory 0x08000000 to 0x0800 FF64KB. This is where your program lives permanently. It is non-volatile, meaning the data survives when the power is removed. However, it comes with two wait states at 72 MHz, which means the CPU has to wait briefly when reading from it. Inside your flash, you will find first the .text section, that is your actual compiled code. Second, the .raw data section, that is read-only constants. Third, the data blur region, that is the initial values of global variables which get copied to SRAM at startup. Last, the ISR vectors, the interrupt vector table. Next one, SRAM 0x2000000 to 0x20004FFF. This is your working memory. It is volatile. That means everything stored here is lost the moment power goes off. But it is extremely fast. Zero weight states. Well, SRAM is divided into four key areas. First, dot data, that is global and static variables that have an initial value. Second, dot BSS, that is global variables with no initial value. Third, stack, that is the one that grows downward, used for a local variable and function calls. The last one here is heap, that grows upward, used for dynamic memory allocation. Next one is APB1 peripherals, which is 0x400000000 to 0x4000FFFF. This is the lower speed peripherals bus, running at a maximum of 36 MHz. It hosts peripherals like UR2 and 3, SPI2, I2C1 and 2, timers, time 2 through time 7, and the RTC. Next one is APB2 peripherals 0x40010000 to 0x4001-7FFF32KB. This is the higher speed APB bus. It contains the GPIO ports A through G, SPI1, UART1, ADC1, and ADC2, and timer 1. The peripherals that need faster response times. Next one is AHB peripherals 0x4001-8000 to 0x4002-33FF. This one is the high-speed bus, the fastest peripheral bus on this chip. It handles critical system components like DMA1 and DMA2, the CRC unit, the flash memory interference, and the RCC, which is the reset and clock control unit. Next, Cortex M3 core 0xe0000000 to 0xe00FFFFF. This region belongs to the ARM Cortex M3 core itself, which contains the internal system registers. Here you will find NVIC, that is the nested vectored interrupt controller. You'll also find SysTick, the system timer, SCB, system control block, as well as DWT, data watch point and trace point. All right. The next one is reserved, unmapped 0xe0100000 to 0xFFFFFFF. This entire region is reserved and unmapped. If your CPU ever tries to access an address in this range, it will trigger a hard fault. So this is simply a zone that processor must never touch. Now, here's the most fascinating part of all of this, and this concept that makes embedded systems so powerful. Notice that flash is at one address, SRAM is at another, and your GPIO registers are yet another address. But from CPU's perspective, they all look exactly the same. Let's set an example here. When you write GPIO O dr is equals to 0, in your code, the CPU is simply writing to address 0x4001-1000. It doesn't treat it any differently than writing to a variable in SRAM. This is called memory map, and it is the foundation of how embedded systems work. Hardware peripherals are not accessed through special instructions. They are mapped into the same address space as your memory, and you interact with them just like any other variable. Here, I would like to state that all this information that I'm sharing is taken from the datasheet, which you can simply find online by just searching for STM32F103C8T6 datasheet. Well, For your convenience, I have attached the link for it in the description. Once you open the datasheet, go to memory mapping, and the information that I just explained here is available with a nice diagrammatic form for your easier and more clear understanding. Furthermore, let's talk about the stack, and this time we are going to understand it deeply. We already know that local variables are stored in the stack area of SRAM. But what exactly is the stack? How does it work? And why should you care? Let's break it down with a real example. What is stack? The stack is a region of SRAM that works on a very simple principle. Last in, first out. Think of it like a stack of plates. Well, you place a plate on top, and when you need one, you take from the top first. The most important thing to remember about the stack is it grows downward. It starts from a high memory address and moves toward lower addresses as more data gets pushed onto it. On our STM32F103C8T6, the stack starts at the top of SRAM at address 0x20005000, and this is called the end of stack pointer. Well, now let's understand the stack pointer. What's the stack pointer? It's the CPU that keeps track of the stack using a special register called the SP, the stack pointer. It always points to the current top of the stack. Every time a function is called, the stack pointer moves downward to make room. Every time a function returns, the stack pointer moves back up, releasing that space. Well, now let's see what happens step by step when this program runs. The first step, that is main function calls outer. The moment outer is called, the CPU creates a stack frame from it. A stack frame is simply a dedicated block of memory on the stack reserved for that function. Inside this frame, we get first A is equals to 10, 4 bytes, B is equals to 20, 4 bytes, and a return address LR 4 bytes. This tells the CPU where to go back after outer finishes. This frame sits at address 0x200004FB8. The second step here is outer calls inner A plus B. Now inner is called with the value 30. The CPU creates another stack frame on top, well, technically below, because remember, the stack grows downward. This frame sits at address 0x200004FD0, and the stack pointer now points here. This is the current top of the stack. Third step, its inner finishes. When inner returns, its entire stack frame is wiped out. The stack pointer moves back up to where outer's frame is, and execution continues inside outer. The fourth step, outer finishes. Similarly, when outer returns, its frame is also released and the stack pointer goes back to where main left off. This is the beauty of the stack. It manages functions calls automatically, cleanly, and extremely fast. Now, the danger, stack overflow. Here's something you must never forget when working with microcontrollers. The STM32F103C8T6 has only 20 KB of SRAM, and that 20 KB has to fit everything: your dot data, your dot BSS, your stack, and your heap, all at the same time. The stack grows downward from the top of SRAM, the heap grows upward from the bottom. If your stack grows too large due to too many nested function calls or large local arrays, it will eventually collide with the heap or other data regions. Well, when that happens, the stack has overflowed. The CPU detects this illegal memory access and immediately triggers the hard fault handler, and that your MCU freezes. This is called a stack overflow, and it is one of the most common and dangerous bugs in embedded systems. So, the lesson here is be very mindful of what you put on the stack. Avoid large local arrays inside functions. Avoid deeply nested or recursive function calls. And always keep an eye on your total SRAM usage. Well, I hope after watching this video about memory in MCU, you would be having a clear understanding about the topic. Thank you for watching this video. And yes, in the next episode, we are taking this knowledge straight to the hardware. We are going to the program GPIO pins entirely from scratch. No HL libraries, just pure bare metal coding. Meanwhile, for more information, you can visit our website, Bare Metal Life. You can find its link attached in the description. Well, until then, keep coding and keep living bare metal life.